Have you ever wondered how the same mathematics can describe two phenomena that seem completely different? A quantum particle tunneling through a barrier, and a solitary wave travelling through fluids or even the atmosphere? Let's begin with something familiar from calculus. For functions like sine and cosine, the second derivative is proportional to the negative of the function itself. This sign difference generates oscillations, motion that repeats back and forth. But for exponential functions, the second derivative has the same sign as the function. Instead of oscillating, they grow or decay. These are two fundamental behaviours, an oscillatory or propagating mode, and an evanescent or decaying mode. This basic observation hides a powerful idea. When a system transitions between these two behaviours, we encounter what mathematicians call a turning point. In quantum mechanics, the Airy equation, together with the WKB approximation, describes exactly this moment, when a wave that was oscillating must suddenly begin to decay. This transition across a turning point is the essence of quantum tunneling. But the story goes further. A recent study has shown that the very same mathematical structure appears in a classic nonlinear system, the non-dissipative Lorenz model. Its governing equation has the same mathematical form as the amplitude equation of the nonlinear Schrödinger equation. And like the Schrödinger problem, the Lorenz system contains turning points, which are locations that separate oscillatory behaviour near the centres from evanescent behaviour near the saddle. Remarkably, the Lorenz model produces a solitary wave or sech-type solution. It oscillates in its core and decays exponentially in its tails, a classical analogue to the way quantum waves tunnel through a barrier. So, what seem like two unrelated stories, a quantum particle tunneling and a coherent solitary pulse moving through a nonlinear medium, are actually connected by the same underlying mathematics. Turning points form the bridge. They unify how systems transition between oscillatory and decaying behaviour, whether we're describing electrons, water waves, or atmospheric dynamics. So, the next time you see oscillations, exponential decay, or a solitary pulse, remember, many of these behaviours arise from one elegant idea rooted in calculus, the sign of the second derivative and the universal oscillatory or non-oscillatory behaviour it generates across physics.